Welcome to the lecture in Philosophy of Science. In the last unit we spoke about theories and theoretical concepts and their distinguishing features, such as that they cannot be empirically defined, for example by like empirical dispositions, but rather theoretical concepts and theoretical properties are the cause of many empirical dispositions. By means of them they can be measured. And for instance, we spoke about the theoretical concept in chemistry of having a dipolar molecule structure. The molecules have a dipolar structure. This is a theoretical concept in chemistry concerning the nature of bondings, of bonds. And it causes a wealth of empirical dispositions like solubility in water, non-solubility in oil, electric conductivity, electrolysis, etc., etc. Then we spoke about the theoretical concept of mass and have seen and saw that also masses are the causes of different empirical dispositions, like for instance the gravitational dispositions to be attracted by other masses by means of the gravitational force. This is one way by means of which, or in which way you can measure masses. Another way to measure masses is by means of their dispositions in regard to inertial forces. So if you accelerate, change the velocity of a particle, so you accelerate the particle, then you need a certain force which is proportional to the mass of this particle. So in this way, for instance, you may even measure the mass of a body, a person, in the outer space where there is no gravitational field. So this theoretical property is a cause of a variety of empirical dispositions. And then we turned to humanities and social science, and you know that one major perspective of my entire account of philosophy of science is that there is a methodological unity in science. I mean, the unity is not perfect. Of course, there are differences between humanities and social sciences on the one hand and natural sciences on the other hand, but basic things are really common. And here I'm trying to demonstrate that a similar situation is found in humanities and social sciences when you think about theories in humanities and social sciences and theoretical concepts which are important there. For also here you have theoretical concepts on the one side, and you have laws of correspondence that relate these theoretical concepts to empirical phenomena, specifically to empirical dispositions, where reminder, an empirical disposition is a certain regularity, a temporal regularity, which is exhibited by certain objects that have these dispositions. So if you put these objects under certain test conditions or antecedent conditions, then they behave in a certain way. So my first example was the concept of intelligence. The concept of intelligence is a theoretical property because it can be measured by means of different intelligence tests. Each intelligence test, like for instance the Wechsler intelligence test, measures a particular disposition, right? A disposition of persons to get a certain score on this test. But intelligence can be measured in different ways. So intelligence is not by definition identical to any of these scores. Moreover, let me generally mention two further differences between laws of correspondence in the natural sciences and in the humanities or social sciences. A second difference is that the laws of correspondence in social science or humanities are not really are entailed by the theory, so to speak, to a lesser extent. So the laws of correspondence for mass really follow from the axioms of Newtonian mechanics. The laws of correspondence for intelligence are not really following from the theory of intelligence. They are just more or less plausible indicators. So, you know, for all theories in the humanities, the indicator, the question which are the right indicators for a theoretical property is not prescribed or determined by the theory. There's more leeway here. So the question, is this really, this indicator, is this a good indicator for the theoretical property which I want to measure, is also called in psychology, for instance, you call it the question of construct validity. So the question here, whether an indicator is a good indicator for a certain theoretical property, is called the question of construct validity. This is one difference, which shows that this is really a difference. It shows that not everything is just the same, right? But still you have these things. Secondly, the laws of correspondence in this field are typically probabilistic or statistical in nature. I mean, a person is not at any time in the same kind of mood, or I mean, there are certain performance factors which modulate your score, which you get in certain intelligence tests or cognitive tests, right? There's just if you have a certain disposition, that means that normally you have a score in this range on this and this kind of test, right? But it's not a strict regulation because there are so many modulating additional factors. So that is the second difference. But apart from these general differences, this example of intelligence is also interesting in certain other respects. So you have here intelligence, and you can really measure it by means of different kinds of tests, right? And then the question is, if this theoretical property is really a homogeneous property, these different indicators, tests for intelligence, should correlate with each other, at least to a high extent. Only if the indicators are really highly correlated, you can really say there's one homogeneous cause, one common cause of all of these things. If they are clustered in some way, so that these correlate with each other and these correlate with each other highly, but these two groups don't bear a high correlation to each other, then this would speak more for a two-factor theory of intelligence. So questions like this typically arise in humanities. And there is indeed, in the intelligence literature, there is exactly this controversy going on. There's one group, one, so to speak, theory. This is called the G-factor theory of intelligence. This says the general factor of intelligence, which is more or less responsible for all kinds of intelligence, although there are certain performance factors, like some people have a better memory than others, or things like that, right? Or there are also is also the social influence on intelligence, like the quality of your education also influences your intelligence, right? How many years you went to school and things like that, right? But I mean, apart from that, the G-factor theory says there's one general factor of intelligence, and if you have a very high G intelligence, so to speak, then this should make your mathematical intelligence high as well as your linguistic intelligence high. On the other hand, there's a two-factor theory of intelligence saying that, for instance, mathematical intelligence and linguistic intelligence, verbal intelligence, are really two distinct factors, right? They are not really highly correlated. Of course they are correlated because there's common causes like the level of education and how long and how well you have been cognitively trained. But if you if you screen off these variables by fixing that, by just investigating people with the same level of education, the same intensity of cognitive training, then the two-factor theory of intelligence would say then there is not any significant correlation between mathematical and linguistic intelligence, while the G-factor theory would say that still there should then remain a significant correlation between these two kinds of intelligences. And so you see here at this example that there's also quite delicate and subtle considerations going on when you in psychology, for instance, have a bundle of correlated indicators, and then you want to explain that by a theoretical property which figures as a common cause, or eventually by two distinct common causes, right? Depends. Okay. Any questions up to here? No. Good. So this is an interesting question of intelligence. Good question also for seeing that there is a need to distinguish the theoretical property and the empirical indicator in psychology and social sciences. Okay. Other examples, right, would be, for instance, theoretical properties like character traits in psychology, like aggression or authoritarian character, tendency to be obedient to authorities. This, for instance, authoritarian character, this sounds like an enormously theoretically high-loaded theoretical term, a very speculative term, but even for those theoretical properties, there have been invented ways to measure them empirically. For the authoritarian character, this was the famous Milgram experiment, right? Milgram was a famous sociologist. He was cooperating with Adorno, who had this general theory that people have this tendency to be obedient, to submit themselves to authorities and do everything what the authority says. And there was this Milgram experiment. People acted as scientists with a white coat and told the test persons that in the course of a very important scientific experiment, a learning experiment, they have to treat a certain person, which actually was an actor, a certain person in a certain way, so that this person should have a high learning success. And this treatment included commands like you should cause pain to this person by certain electric voltages, by certain electric currents which you induce to this person, and the person which was actually an actor, not a real person, really yelled. And still, the test persons, the two test persons, did what the scientists required from them, because they said, well, it's no problem, it's harmless, you can do that. And then the person did it, right? Just because the authority told them to do it. And afterwards, they were shocked that they really did it, right? In post-interviews. I don't understand. The people said, I can't understand why I did that. It just, this expert had such a strong authority and appeared so trustful to me and reliable that I simply believed him. Yeah. However, this Milgram experiment is really a famous experiment, how you also in social sciences those can give empirical meaning to theoretical concepts of very abstract high-level theories, right? How you can break them down, so to speak, to the earth of empirical experiments, right? Okay. Other examples in social sciences, if you want to measure the attitude of people, right? For instance, in lots of studies of Ronald Inglehart, they want to measure the cultural values which people have. Ronald Inglehart is famous for this kind of studies, and for instance, when sociologists want to find out to which degree are white US Americans conservative, so they want to measure the conservativeness of a person. And then of course you have the same problem. What are the right indicators for conservativeness, right? Do you ask people questions like, do you share Christian values? Right? Are you religious? Is that an indicator of conservativeness? Or do you ask them values like, do you avoid frequent changes in your life? Do you want everything always to behave the same in your practical life? Don't you like changes of residence or whatever? I mean, practical conservativeness, right? So what are the right indicators here? And also here the question, of course, arises then, is conservativeness really one factor of attitude, or is it a homogeneous property or not? So these are the typical questions which are associated with theoretical concepts in the social sciences and in psychology. There are two methodological rules, two important methodological rules, which when one makes empirical tests or experiments in humanities and social sciences, which one should follow. These rules concern the choice of tests. The first rule is avoid distortions because of biased indicators. What do I mean by that? An indicator is biased if it introduces a hidden variable which measures something else than the theoretical property which you intend to measure, which introduces a deviation, a bias. An example is self-assessment. If you measure the attitude of persons concerning their own values they have, or their attitude, by asking them, what do you think you are, what is important for you, what you really measure is the self-assessment of persons, right? So if you, for instance, ask how important for you is environmental protection, so protection of the environment, environmental protection. How important is that for you? Then, for instance, most people will say, well, it's very important. On a scale from 1 to 1, well, it's very important, of course. How important is it that you want to save the forests in Europe, or that you want to avoid pollution of air, and so on? It's very important, right? Everyone wants to be wants to have a good ecological conscience. But psychological studies confirm that most people tend towards an exaggerated attitude towards themselves. They see them much more positive than they really are. They have a bias towards positive self-assessment. So if you ask, for instance, people, what would you think, are you more intelligent than, or better than the average, or worse than the average in some respect? Then 80% say, or even 90% say, I'm better than average, right? So it can arithmetically never sum up. So also here, in this respect, self-assessment may be really may cause a distortion of the result. And some clever economists, for instance, invented ways to test, to find out for instance, attitude towards environmental protection by other means. For instance, by a question asking, how many % of your income would you be willing to spend as an environmental tax? 5%, 2%, which is then used to protect the forest or whatever, to clean the air and so on. And in this questionnaire, although the questionnaire was of course anonymous, it was also said that the result of that questionnaire will be handed over to politicians, and so that if really 80% say, yeah, 5% is absolutely okay, maybe that could have political consequences then. And if you do this experiment, then you see that the environmental consciousness or environmental attitude of people is much lower, right? And really, I mean, they don't really want to spend much money on that, right? Although it's very important. So this is an example of how you can avoid a biased indicator by clever experiments or clever questions, right? By indirect questions and so on. The second methodological rule is the following. You often have a situation where you have really a very general theoretical concept. For instance, in case of Piaget's, Jean Piaget was a very famous psychologist. He was the originator of the theory of cognitive development in children. He was a psychologist and a philosopher, so to speak, and came up with his developmental theories of cognition in the beginning in the 40s and 50s of the last century. And one of his very theoretical notions was the ability of children to take over the perspective of another person, right? To switch perspective. I can imagine how, for instance, this room looks from your perspective where you are sitting. That is a certain ability. Take over perspectives of other. Perspectival change, it's also called. And he tested this ability to switch perspectives with a quite complicated test, which he always used the same test for that. And he never came to the idea, he never had the idea that you could test this perspectival question also with very different other kinds of tests, right? And when later on in the 70s, psychologists tested the very interesting Piagetian question with other indicators, with simpler perspectival tests, asking like, how does this box, which has different colors on each side, look from the perspective of Susie, who sits there, and how does it look from the perspective of Peter, who sits there, and so on. I will speak about that in much more detail in the next lesson, in the next lecture. But when these psychologists did these replication studies with other indicators, Piaget's major theses were no longer tenable. So what you really should take, and that led to very interesting developments in developmental psychology, in the psychology of cognitive development. So what you should really follow here is the device that if one and the same theoretical properties can be measured by different and equally plausible indicators, you should really test it with all of these indicators, right? That is really important. Because if that is not the case, right? So if you assume there is a certain property phi, right? And there are some indicators like a certain cognitive ability of a child. All these indicators are equally plausible. But then your theoretical claim works just with these indicators. And your theoretical claim yields false predictions for these indicators and only correct predictions for this indicator. What does that mean? That means that there is something which you really didn't understand here. There is some, so to speak, distinction here in the nature of the objects which you want to study, in this case children's intelligence, children's understanding of the world, which you really don't understand here, because there is no distinction in your theory, but there is distinction in the empirical results. Okay. So this is the second methodological rule. Okay, good. So this concludes my my explanations about theoretical concepts in humanities and social sciences. So any questions up to now? Yes?
When would you say that there are several theoretical concepts under consideration and that the tests are for these different concepts? And when would you say that it's some kind of the tests are not reliable, or the disposition tests are not reliable? You know, I mean, you said if you have one theoretical concept, then 3 reliable tests should come up with the same empirical results. And when would you say it's the test is not reliable, but there is one theoretical concept, and when would you say there are several theoretical concepts but reliable? Yes,
this already goes beyond what I'm telling in this basic course, but whenever you have empirical dispositions, indicators, E1, I2, right, I3, they are correlated. So when you can exclude that they can, so this common cause abduction, I call it, so you so to speak, generate the hypothesis of a theoretical property here by what I call a common cause abduction. The theoretical property is the common cause of these correlated dispositions. This is only justified if a more parsimonial causal explanation can be excluded, namely that one indicator, one disposition is the cause of the other, and this is the cause of that. If disposition, in the case of dispositions, but I cannot go into detail here, if the antecedents of the disposition are independently variable, then this can really be excluded. So there must be, if the causal Markov condition is really correct, then there must be some kind of common cause or common causes. So if that can be really concluded that they cause each other, so there's no so to speak, theoretical explanation needed. But if that can be excluded, then there must be a set of common causes which produce this correlation. So then the question is only, what is the structure of this set of common causes? If they are highly correlated, if they, it's also a cluster analysis is a technique by which you can also do it. Another technique is factor analysis. So if you have really these indicators which are highly correlated, all of them usually, more or less, then you say, well, phi is a common cause of all of them. A statistical common cause, there are some modulating these further factors which are small. So, right. But if they cluster into two groups, right, then you would say, well, no. If the correlation between them is really small, maybe a little, but small, and that is much higher, then you would say, well, it's better explained by two causes, right? A technique by which you do that is factor analysis. And factor analysis. So then you would say this indicator doesn't measure this property, but it measures just this property. And then you have, yeah, that is very good. You must generally always be careful in interpreting thus unifying explanations in a realistic causal way. But I mean, if certain conditions are met, then the interpretation is justified. And I mean, yeah. Other questions? Okay. Next, I will explain to you some basics about the structure of scientific theories. Some basic distinctions, some basic conceptual distinction which I will illustrate later on by means of examples, namely by means of two examples of scientific theories. One will be classical mechanics, Newtonian mechanics, and the other will be the Piagetian theory of cognitive development. But first of all, the basic distinction. First of all, you can distinguish between and within the language of a theory. There I distinguish between the total language, which I also call, or is also called, the total theoretical language, but this total language contains both empirical or non-theoretical and theoretical concepts. Right? I mean, this is although these distinctions which you find, for instance, in this book of Mailer and Nini Lotto in the 70s, a nice book on the structure of scientific theories. 1973 or something it appeared, or 1974. Where they make all these nice distinctions. They make the things general which you find not as general as in these books already in Carnap and Hempel, and also the structuralist theory guys like Snead, and then learn from that thing. So you have the theoretical language, the total language, which contains both kinds of terms, and you have the empirical sub-language, which is very important. And then a theory in the so-called statement representation of the theory, it's represented by certain statements which a theory makes, and especially by the axioms of the theory. In the theoretical language, you have on the one hand purely theoretical laws, right? Theoretical laws are laws which just connect theoretical concepts of the theory. Mostly they are axioms. Well, I explain that later with axioms and theorems. Then you have laws of correspondence. They connect theoretical concepts with empirical concepts. both of them are formulated in the total language, in the theoretical language, right? Which contains theoretical and empirical concepts. And then you have the so-called empirical content of the theory, which is a very important notion and is expressed in that form, the empirical content of theory T. And this comprises simply all empirical consequences. So all sentences follow logically from the theory and are empirical in nature, so are only formulated with empirical concepts and logical concepts. And what is of course important in the assumption is, so to avoid a kind of irrationalism or incommensurability claim, in the sense of a radicalized version of Kuhn and Firearm, to avoid that you need, and we make the assumption that different competing theories, as we know from the last lecture, they have different theoretical concepts, right? Of course, Newtonian mechanics and relativity theory have a different concept of mass and so on, right? Phlogiston theory and oxygen theory of combustion has a totally different concept of fire and heat, but these competing theories have a common empirical sublanguage, right? Because the empirical concepts, or the pre-theoretical concepts, as you also call them, they are common to both competing theories. They are theory neutral. And so their consequences in this empirical sublanguage can be compared, and so there's a rational comparison between the two competing theories possible, right? I mean, if one theory has a higher empirical success, so to speak, than the other theory, then the one theory is better confirmed than the other, even if there is no direct way of comparing the two theories at the level of their theoretical concepts. That is an important function of this distinction here between the theoretical part of a theory and its empirical part, because the empirical part is common to different theories. Okay, so the empirical language, I mean, is common to different theories. Of course, the empirical content may differ, right? And is different, must be different in order to discriminate in terms of confirmation between the theories. Okay. Then the other distinction is between the axioms and the consequences of a theory, consequences or theorems. The axioms, in the way I understand them here, are just all non-derived assumptions or principles of the theory, and the consequences are those which are derived from others. The theoretical laws are typically axioms. The laws of correspondence are axioms, but also very often theorems, consequences. For instance, all these measurement laws, like measuring mass on the balance beam, is not an axiom in any physical theory, it's a consequence. Also the laws of lever, the Archimedean laws of levers, law of levers, is not an axiom of Newtonian theory, but a consequence, right? I mean, the axioms are much more general. So this was a mistake an error of the late Carnap, by the way, because the late Carnap really thought that the theory consists of a certain correspondence part and a certain theoretical part, however he called it, I don't know, right? The axiomatic, the theoretical axioms and the correspondence. So it is formalized in that way, but that's not really the case. Most laws of correspondence, in the sense of Carnap's, are derived from the axioms of the theory. But that doesn't change anything in the general approach here. It's just an important remark to apply this framework here to real case theories, right? The empirical content of a theory is usually theorems, right? A theory almost never contains a purely empirical assumption. All these empirical assumptions are derived. Sometimes it may contain, but not necessarily. Okay. So axioms versus consequences, and then the third and most important distinction for the question of testing theories is the distinction among the axiomatic sentences of a theory. So with axiomatic sentences I mean all non-derived sentences. They need not be they do not comprise only the core principles of the theory, but they may also be auxiliary assumptions, which are axiomatic in the sense of not being derived, just basic assumptions. And you can order these axiomatic non-derived statements of a theory according to their importance. And this goes back to Imre Lakatos and makes up Lakatos' famous refined methodological falsificationalism. So his refined theory, it's not the falsificationalism anymore in the sense of Popper, but his account of research programs, which is really a very, very important development in the post-positivist philosophy of science. So Lakatos said, and again, this is only here the overview, and and I will illustrate this in detail at the end of my examples later on. So Lakatos said that among the axioms of a theory, you can distinguish between the core and the periphery. And this distinction is, of course, more or less gradual. So for going from here to here, there's a gradation here. So the core axioms consist of theoretical axioms and central laws of correspondence. They, so to speak, what is here important? They define the identity of a theory. For, you know, a theory now, being a system of statements with a certain domain of application and a certain explanatory promise and going along with a research program, is now a historical identity, right? So there might be historical changes of one of the same theory, right? But what makes up the identity of a theory T1 now is the core. So the core, as long as the core is the same, Lakatos says that we speak of the same theory, which undergoes certain peripheral changes. The periphery of a theory, on the other hand, consists of less important assumptions. There are of course certain intermediate, as we'll see then, certain intermediate statuses, like special laws of correspondence. And special laws of correspondence are somewhere in the midst here, between the inner and the outer sphere. And the least important kinds of statements of a theory are what one usually calls auxiliary hypotheses. And I will give you examples soon, right? Auxiliary hypotheses, they are usually always changed. They are changed, say, every 3 years, right? Every year people come up with different auxiliary hypotheses. But while cores, if a core of a theory is changed, that corresponds, a core is like a paradigm in a Kuhnian sense. But it's a rational version of a paradigm. There is no incommensurability here, no strong kind of incommensurability here given. But if a core of a theory is changed, that corresponds really to what Kuhn thought of as a paradigm change. So that happens very rarely in the history of science. Okay. So these are the important notions which I will explain to you at the end of examples in the following. So if there are no questions, are there? Then I go on and tell you certain methodological characteristics of good scientific theories, which are also explained here first logically, on a logical level, and then I will illustrate them at the end of the example. So, as I said, a feature of theories is their system character or holism. Generally speaking, holism or system character means that the important properties of theories, the important epistemic, methodological and ontological properties of theories are properties of packages of sentences, so are properties of systems, while single statements, single principles of a theory don't have interesting properties. There are three kinds of holism. The first is the holism of meaning. And we spoke about that in the last lecture. The holism of meaning simply says that the meaning of a theoretical concept, such as mass, is not given by a particular single definition and not given by an in particular not given by an empirical definition, where you try to reduce it, where you try to reduce it to an empirical disposition, but it's given by the theory to which the concept belongs. Of course, it may be that special theoretical concepts are semantically explicated by more general theoretical concepts, but the fundamental general theoretical concepts, at least their meaning is explicated by the entire background theory, or more properly, at least by the core principles of this background theory, the core principles, right? That is the holism of meaning. And I explained it at the end of the concept mass. Then there's a holism of empirical content. What is the holism of empirical content? It means that, for instance, assume a theory has two axioms, A1 and A2. The holism of empirical content means that the empirical content of A1 may be empty, and the empirical content of A2 may also be empty. But surprisingly, the empirical content of A1 and A2 is large. Right? This is the holism of empirical content, right? And this is very important discovery. So if you put one axiom of a theory has no empirical content, the other one has no empirical content, but if you put them together, whoops, they produce empirical content. That is was important discovery. Connected with this is then the next thing, the holism of theory testing or of theory falsification, right? Because if that is the case, right, assume that is the case, then, well, A1 alone, the axiom A1 alone doesn't imply any empirical prediction, but A1 and A2 implies together, they imply a certain empirical prediction, say P, right? So they imply it. But now, assume you observe not P. So then you know the conjunction of A1 and A2 is false. There must be an error here in this conjunction, but you don't know, is this false or is this false? You don't know which part you should give up, right? And in particular, if this axiom A1, for instance, is a theory core, and A2 is a peripheral auxiliary assumption, and you always have these two different kinds of premises here when you derive a prediction from a theory. You always have some premises which are core assumptions, and some premises which are auxiliary assumptions, right? Then the holism of theory testing tells you, well, we are never forced to give up the core assumption. You can always give up some auxiliary assumption and change it by some other auxiliary assumption. So this is the holism of theory testing, and I will illustrate that for you in a minute. So you see that all this is really related, right? It's really strongly related. Now, you might think that the holism of empirical content, well, first, next thing. So the holism of empirical content is also related to what you call empirical creativity. So what I wrote down here on this slide, that the empirical content of two axioms might be empty, but together they have empirical content. That is also called empirical creativity. If you join the two axioms, they produce, they create new empirical content. Right? So some people are surprised how that may happen, right? That the empirical content is creative in this sense, but it's absolutely simple. Assume, for instance, the axiom A1 has the form for all x, if there is a certain empirical property E1, then there is a certain theoretical property phi. This axiom has no empirical content, right? Assume that the second axiom says for all x, if x have the property phi, then they have the empirical property E2. These axioms has also no empirical content, but together they imply the empirical prediction. Whenever an x has the empirical property E1, then it has the empirical property E2, and that is their content which they produce together. So it's as simple as that. Of course, in science, when you study Newtonian, when When I will turn soon to the Newtonian axioms, and you have quantitative axioms, then it's not as simple as here, but the principle is the same. The principle is again that if you have two axioms, no empirical content, what is required, of course, it's the same, that they share a theoretical concept. In that case, phi. They must, of course, share theoretical concepts. Otherwise, that cannot be. Empirical creation is only possible if the two empty concepts share theoretical concept. The empty axioms share theoretical concepts. Then you join them. Then you produce no empirical content. And that is a really important property of, so to speak, theories and parts of theories in regard to their empirical content. Yes?
It could also be that we have two laws or axioms which already have some empirical content, but when put together they have an additional empirical content, right?
Yes.
So this would be a good case for interdisciplinary work.
Yes, definitely. Of course, that can also be that you have two parts, they have already some content, but the empirical content of their union is stronger than just the union of their empirical contents, or the logical closure of the union of the empirical contents. There are some nice logical theorems which you can prove. Absolutely right. I mean, this little logical observation really caused a significant change of the philosophers of science in the tradition of logical empiricism towards metaphysics. That was discovered recognized by Hempel in a paper in the 60s or so on. You know, because the verdict of the classical empiricists to speculations, let M be a metaphysical speculation. It has no empirical content, right? And the verdict of Hume was, then committed to the flames. It's useless, right? Because it has no empirical content. And that was quite the attitude of the positivists before the Second World War. Right? But in the post-positivistic phase, so 1915s and so on, then it was recognized by means of these observations that that doesn't follow. It may well be that you have one metaphysical theory M1 and another metaphysical theory M2. Both are void of content, but if you join them at a later time in the history of ideas, you get an empirical contentful theory out of their conjunction. Or you may join a metaphysical theory with an established scientific theory, which then increases empirical content. So you cannot say that a metaphysical speculation, just because it has no empirical content, is, so to speak, fruitless, right? It is contentless, that is clear, but it can be worthwhile to pursue that metaphysical idea, because it may be that in a later stage of science it achieves empirical content by being conjoined with other pieces of ideas, right? So there is no strict and one and forever discrimination between scientific, empirically contentful theories on the one side and metaphysical speculations on the other side. That is historically dynamic now. And that was quite important. Okay. Final point. Two final properties of theories are these two. Global unification power and novel predictions, cross-sectional predictions. What do we mean by that? Global unification power means that a theory, typically a good scientific theory, is able to offer unified explanations for phenomena which come from different, from qualitatively different domains of application. For instance, for what the Newtonian explanation is so famous, that it unified two fields which formerly were separated. From Aristotle onwards, there was this theory that there are two kinds of physical bodies: earthly bodies, bodies on earth, and celestial bodies, bodies in the eternal heaven, right? And these earthly bodies and the celestial bodies have different physical dispositions of movement. The earthly bodies follow in a straight line to the center of the earth, if you let them follow. They tend towards the center of the earth, which was also seen as the center of the universe. But the celestial bodies have a kind of perfection. Their inner disposition is to move in perfect circles, because a circle was thought to be a perfect geometrical figure. I mean, that was then already a problem for Kepler. I mean, this theory held on until the end of the Middle Ages. Even Kepler held on it. And when Kepler discovered that the trajectories of the planets are not perfect circles, right, but they are ellipses, less perfect than circles, then Kepler had a problem with that. In his Mysterium Cosmographicum, he tried to explain that by assuming that a planet is less perfect, isn't really fully perfect like fixed stars. Stars are perfect, but planets are less perfect, so they move in elliptic trajectories. But I mean, even Galilei, right? Galilei assumed that there is a circular impetus, right? So that stars or planets can move in circles without any need of force here, right? So you really see there was not at all, not in the slightest way, a common explanation here, any mechanical, any dynamical explanation of these very different dispositions of movement. And Newton unified that just by assuming this gravitational force, by assuming that first the principle that every change of velocity, be it a change of amount of velocity or being a change of the direction of velocity, needs a force. And so this causes a circular movement, causes a centrifugal force, which must be compensated by a centripetal force, and that must be the force of the sun, which holds the planets on its trajectory. And so he discovered the law of gravitational attraction. And of course, this gravitational attraction must act within all kinds of masses, and so he come up with this absolutely bold conjecture that between all kinds of bodies there is this gravitational attractions, which is, by the way, an interaction because it goes in both directions. So in this way Newton offered a unified explanation of a wealth of phenomena which he unified these two realms of earthly bodies and celestial bodies, heavenly bodies, right? And he offered a unified explanation of all these phenomena, of movements of bodies in the gravitational field of the earth, of parabolic trajectories of projectiles, of the trajectory of course the law of falling bodies of Galilei, the laws describing the gravitational pendulum. All these things followed from these few axioms, the laws describing the movements of planets, elliptic orbits around the sun, but also the laws describing, say, for instance, the trajectories of arbitrary bodies like comets, right, or rockets shooting up in the outer space or whatever. So the development of classical mechanics was an absolutely rich research program on all these classical physicists after Newton enlarged the theory and with a tremendous success. Only then, in the beginning of the 20th century, then there were these discoveries which set up the limits of Newtonian mechanics. When you go up to very high velocities, then relativity theory comes into place, and when you go to very tiny particles, molecules of molecule size or atomic size, then quantum mechanics comes into play. But for all moderate-sized objects and moderate distances, still classical mechanics is a very good very approximately true explanations of the behavior of physical bodies. So this is global unification power, and related with that is qualitatively novel predictions. This just means that you can predict phenomena which are qualitatively different from those which you have observed before. That is meant by novel prediction. And that is also a typical feature of theories. Like in the case of Newtonian theory, I mean, if you're an empirical inductivist like Aristotle, whenever you throw something upwards, it will fall down again, right? So this is just a law of falling bodies. Whenever you throw something in the air, it will come down. But I mean, Newton predicted from the classical Newtonian theory, it follows that if you throw something with a high enough velocity into the air, it will never come down. It will enter maybe in an orbit, or it will leave the gravitational field of the Earth, and move away in outer space. Right. This is a perfectly anti-induction, so to speak, from an empirical viewpoint. That you never experienced it, right? No empirical inductivist would conclude that if the velocity is strong enough, right, then it will not come down. But a theory can do that, and that is the most drastic example of a novel prediction. A theory can do that, because from the intrinsic theoretical model which you have, you can really produce qualitatively novel phenomena which you don't get from empirical prediction. I mean, there are much simpler cases than that. For instance, last lecture I spoke about this chemical theory concerning the solubility of substances in water or in oil. And there I told you that if you have a theoretical model of solubility, then you have the prediction that if some substance soluble in water, you have some substance which is totally new, and you see it is soluble in water, then you can predict that it is not soluble in oil from the chemical theory, right? Without ever having put it into oil before. So that's already a simple example of a novel prediction, right? You don't need to put it into oil. You can predict it from its solubility in water. So this is meant by cross-sectional predictions, that from the behavior of certain objects in one domain you can really infer something about a qualitatively different domain. That is also a typical property of genuine theories and theoretical models, as opposed to simple empirical laws and hypotheses. Okay. Any questions up to now? Yes?
I wonder if you could say a bit more, this is sort of going back a bit more about what goes in a Lagrangian picture, what goes into the periphery.
I come to that just now, at the end of the example.
Okay.
Maybe you repeat the question then?
Sure.
Because come to it right now. Some auxiliary hypotheses are much more special than certain special laws. So there's really difference in character here. There are some ceteris paribus assumptions here. Okay. So now I will illustrate this at the end of my first example. The example of Piaget's psychology will come next lecture today. I speak about Newtonian physics. So this is my first example. So the example is now, how do we derive, for instance, an empirical prediction concerning the trajectory of a planet from classical physics? Okay, so there are these core laws. First, the total force acting on a body X equals its mass times its acceleration at a given time. That is a second Newtonian axiom, and this axiom has no empirical content, because total force and mass are theoretical concepts and acceleration is the only empirical concept. So all what this axiom says, write it now in a more mathematical notation, that acceleration acted on x at a certain time on t equals the force, which is also a vector acting on x on t, divided through x's mass. So the relation of these theoretical constants equals this empirical property here. That is what the first axiom says, and it's clear, and this was shown in detail, in minute detail, by means of modern theoretic considerations by Schurz. Right? This is what he's famous for. The logical structure of theoretical physics. Schurz showed this. However, the acceleration of given bodies is, you can always invent force and mass functions so that they satisfy that. Right? Okay. The second core law of classical physics is force equals counterforce. That may actually have different versions, but the simplest version is just if you look at the gravitational force, whenever there's a force acting from one body towards another body, say an attractive force, then there is an equal attractive force acting from this body to that body. For instance, that is one version of that. Actio equals reactio. Action equals reaction. Snead, in his book, argued that if you join these two core laws together, then you get already empirical content. For instance, you get the law of conservation of momentum, which describes the inelastic collision, right? That is what you get, because the momentum of a given particle X, if you change that momentum, then that is in a collision, the impulse, the momentum is changed, and this is equal or proportional to the force acting on this body. So by applying the force laws, you get the laws of conservation of momentum. It's very famous. And then you, for inelastic collision, for instance. But of course, this is not really strictly true only if you add an auxiliary hypothesis, namely that on these two bodies which are colliding, no other forces are acting on them. But this is the auxiliary assumption which you have to make in addition to get this result. But for if there is an additional gravitational field, of course, that may be different, right? Only if there is a force free. And similarly, Snead argued that from these two core axioms, you can derive the laws of levers, right? This is true, but also only if you assume that the forces acting on both sides of the lever are exactly equal. This is an auxiliary assumption which you need. And generally you always need to get empirical content out of physical theories. This is not only true for classical physics, it's true for all theoretical laws of natural sciences. It's even true for the theoretical laws of population dynamics in evolutionary biology. It's true for quantum physics, it's true generally. And I describe these things in much more details in my book here, in Philosophy of Science, a Unified Approach. But you see, you have this notion of total force here, so you always need certain auxiliary assumptions telling you this and these forces are present and nothing else, right? Okay. Good, but the point here is, if you join these two core axioms of the theory, together with a certain auxiliary assumptions saying nothing else, no other force is present, you get a little bit of empirical content. The conservation of momentum and the laws describing the laws of the law of levers. But it's still not so big. The real explosion, in a metaphorical way, the explosion of empirical content takes place when you join this now with a special law describing a particular kind of force, namely, in this case, the law of gravitational force, saying that the gravitational force between two objects x and y is proportional to the product of their masses. This is a gravitational constant here, divided through their distance, right? So, you can have it also in a vector notation, then it's a little bit more complicated, but there's a special force law. If you join this now with these two core axioms and add further auxiliary assumption about which gravitational forces are present, then really the empirical content explodes. So the fourth kind of premise is a premise A1, A for auxiliary, S for special law, C for core, right? A1 says this and that gravitational forces are acting upon the body X, which is, we assume, a planet, and nothing else. Usually, in all standard calculations, you usually assume that it's only the gravitational force of the sun which exerts a significant influence on the planet, and you neglect every other gravitational forces, maybe that of other planets or whatever, because they are so small, so little compared to the gravitational force of the sun. So this is a standard premise set. And this answers maybe your question, because you see, if you draw that in the Lagrange scheme, then you have C1 and C2 somewhere here, S, you have S1 somewhere here, and A1 you have totally at the outside. Auxiliary assumption A1 is what I also call a system condition. It speaks about a particular physical system, right? These kind of auxiliary assumptions say list the gravitational forces which hold in certain kinds of physical systems, or list all kinds of, say, some physical parameters like forces in classical mechanics which hold in particular kinds of physical systems. This gravitational force this is also a special law, but it's much more general, right? It holds in all physical systems where gravitational fields are involved. But it's still, this S1 is still more special than these core laws, right? Okay, now, from these four premises, there follows in a famous way, which you learn if you're in a physics class in high school. In a physics course, you learn this, I think. This leads to a simple differential equation, and you learn it also in the first semesters when you study physics. It leads to a simple differential equations. The solutions of these equations give you all possible physically allowed paths or trajectory of the planet X as a function of the time and as a function of the initial condition of the planet. So, for instance, if there's a certain mass and there's a planet with a smaller mass, then this tells you, well, all these trajectories are allowed, right, with a certain function. S is a function of t, right? And if you know the initial position and the initial velocity of the planet, right, then at a certain time point, then you can predict from that the concrete trajectory of that planet for all times, right? So that is how it works. Well, and that is how famously the classical mechanics derived all of these Kepler laws describing the trajectories of planets. Any questions up to this point? Yes?
I mean, Newton had three main principles, I think.
Yes.
So
the first follows from the second. The first says a force-free body moves on straight line. And the second says acceleration times mass equals the sum of all forces. So the first follows from that, because the force moving in a straight line means acceleration is zero. So then the sum of all forces is zero. So I say it also in the books, therefore I only present the second law and the third law and not the first. Some people are controversial about that point, whether really the first axiom follows from the second. I mean, but in standard presentation as it presented in today's physical textbook, that is it's seen. Right? So, yeah.
And what's your opinion about the discussion that the first principle is just some kind of definition of the concept of total force?
Well, that's certainly wrong, because of that's my opinion, that cannot be, because the force is the cause of the acceleration and not the definition. That's just a constructive realistic picture of theoretical properties in science. I mean, I already said that mass is not identical with all these dispositions. And the same reason force is not identical with all these positions to move, right? That is my position. It is a cause. I mean, yeah. But
formally you could just consider this.
Yes, Charles Sanders Peirce has this famous discussion. Charles Sanders Peirce has famously in his 80s-70s papers, I don't know exactly when, he had the position of this totally instrumentalistic pragmatist, where he says, it doesn't make any difference whether I define force just to be the acceleration. So force is identical with the acceleration of a certain body with a certain mass. I mean, I saw this. Peirce doesn't speak about how masses are measured. Somehow it seems that is an empirical concept. I don't know. That is a problem of its own. But given masses are given, then force, he says, is just identical with a certain acceleration. But later on, the Peirce in 1905 changed his position, right? And I mean, you know, the crucial point again is, what refutes this instrumentalistic reading is that one and the same theoretical property is a cause of different dispositions. For instance, gravitational force is not only the cause of accelerations, it is also the cause of many, many other dispositions. So I mean, it would be somehow arbitrary to say, well, that is a definition of force now. And the same holds for other forces. I mean, acceleration can be caused by other kinds of forces, not necessarily by gravitational force. Think of electrodynamic forces. An electron tube, well, an electron ray. Here the acceleration of the electrons is caused by the electric force, by the electrodynamic force. So should we now define electrodynamic force also by acceleration? But then it would turn out that gravitational electrodynamic force would be the same, because both of them are defined as m times acceleration, mass times acceleration. That would also make no sense. So on all of these reasons, as I said, there is this many correspondence between theoretical properties and empirical dispositions, and that goes not only for mass, it goes also for force. You know. And on all of these reasons, I would say that the constructive realist position, I mean, I'm not a strong realist, but I would say if there is a strong, so to speak, unification achieved by the theoretical concept, which is in accordance with these causality principles, then the easiest assumption is to assume, well, there's really something there which causes that. That's it. But who wanted to say something? What? Okay, yes.
So I think maybe you could say if mass is given, the total force could be somehow defined through this. But I think the problem here is that mass is already a theoretical concept.
Mm-hmm.
I think this is a beautiful example of the holism meaning.
Yeah.
Because only together these theoretical concepts in this whole theory start to make sense.
Yeah, the total force. But if the total force is the sum of two forces, one is mechanical and the other is electrodynamical, which you have in certain experiments where bodies have both mass and electric charge, then what do you do then? I mean, you define the total force with the acceleration, but how do you get the components? So it's different to have this as definition.
Empirical laws or an additional law at least.
Yeah, it would be an additional, Yes. But now I come to a different question, namely to the question holism of theory testing. And this is concludes today the part this is the last part of my lecture today. So the theory, these premises together are also called the theory version, like core, special laws, auxiliary hypothesis. They imply a prediction now. And if this prediction turns out to correspond with the observations, everything is fine. For instance, the predictions of the orbit of Mars corresponded to what Tycho Brahe and later astronomers observed empirically with the telescopes. The telescopes always get better and get better, and everything was fine. And in that case, the scientists conclude that, well, the theory as a whole is corroborated. But the problem arises when there is a deviation of the observation from the prediction. What do you do then? There were indeed deviations from the prediction of Newtonian planetary theory. And here we come to the crucial point of Kuhn and Lakatos. I mean, Kuhn already said that if the theory conflicts with the data, the scientists never give up the theory. It's just somehow they are able to immunize the theory against conflicting data by certain ad hoc hypotheses. And this turns out to be true in this reconstruction, although it is not as dramatic as some people think. It is true because of this auxiliary hypothesis, because of this nothing else clause, which is also called the ceteris paribus clause. So this nothing else clause just says it's a ceteris paribus clause as long as there are no further factors present. Ceteris paribus. Nothing else. And of course, just by doubting this little clause, nothing else, you can save the theory from collision, from logical inconsistency with data. And that is even not unreasonable. I mean, that is not really necessarily unreasonable, as you will see now. In 1846, Adams and Leverrier detected that Uranus, which is an outer planet past Jupiter, deviated from the predicted, the orbit of Uranus deviated from the prediction by classical mechanics. So why? So the ad hoc postulate was indeed, by these two astronomers, that there must be, we don't doubt that Newtonian theory is wrong, I mean there must be a perturbing planet, which so far has not been observed by telescope, and they call this planet Neptune. You know the planets circle around the sun in different periods, in different circulation periods. So sometimes they come close to each other, and with different velocities. Sometimes they come close to each other, some certain times, and then they come very close. It might well be, right, that say the orbit of Uranus gets a slight deflection, right, because some other planets has come quite close to it just at that time. And Newton already developed recipes by means, mathematical and physical recipes by means of which you can approximately calculate the mass of such a hypothetical perturbation planet, right? So these Adams and Leverrier also said, well, so we conjecture there should be a disturbing planet, too small to be seen with our present telescope, but it should be somewhere in this region at that time and should have a mass of that size, right? Okay, now, so this is an example of an ad hoc hypothesis. What makes the hypothesis ad hoc, as you call it, is that they introduce it ad hoc, yeah, just for the purpose of reconciliating the theory with this anomalous data, right? Avoiding the conflict of the theory with the data. You postulate it. That's the whole purpose. Okay, so is it an immunization step or not? Right? Does it mean, what does it mean? Well, see, in the history of in the actual history of physics, indeed, Neptune was independently confirmed. The existence of Neptune was independently confirmed later on, some 10 years later on, with better telescopes. So this was celebrated as an enormous success of classical physics of celestial bodies, a breakthrough, right? Because this was a qualitatively novel prediction too, right? There should be some planet which is so far didn't observe. I mean, if you can really predict such a thing, that's a great success. So you see that as soon as Neptune was independently confirmed by stronger telescope, of course, the Neptune hypothesis is no longer ad hoc. So the ad hocness of a hypothesis is a historical feature. A hypothesis may be ad hoc at a certain time, but may lose its ad hocness at a later time when it becomes empirically testable. So this was the example with Uranus and Neptune. But I mean, the immunization thesis would say, well, you can do this always, right? Indeed, in 1856, Leverrier recognized another deviation from Newtonian prediction, namely in the orbit of Mercury. Mercury is that planet which is closest to the Sun, right? Of all of that. Mercury, Venus, and then the Earth. So, the orbit of Mercury was somehow banded, and they postulated a further perturbing planet. They called it Vulcan. Vulcan as a perturbing planet of Mercury. By the way, what I'm telling you, these nice stories, makes up a major part of Imre Lakatos' famous paper on the research programs, falsificationism and the methodology of research programs. Imre Lakatos. So also these examples are from him. Well, in this case, Vulcan was never confirmed, right? So even with the strongest telescopes, they never could find such a planet named Vulcan. which they called Vulcan. They could never find it. But there should be, the planet should be there in order to explain the deviation of the orbit of Mercury. So what should we do? Lakatos writes that in principle you can go on in defending Newtonian mechanics even if Vulcan is not observed, because you can invent additional perturbing factors which explain that. For instance, you can assume that Vulcan is hidden behind a cloud of cosmic dust, right? So that you cannot see it with the best telescopes, right? I mean, I don't know. Maybe later on you can send an unmanned space shuttle to Vulcan to see it, but then maybe the space shuttle gets destroyed, and then you say that maybe there are certain creatures living on Vulcan who are just destroying all space shuttles going to Vulcan, or I don't know. In any case, you can go on with perturbing factors, inventing more and more of them, just to explain why you can never discover the existence of Vulcan. And that is basically the story behind this immunization problem. But what really went on is, of course, the following. And this is also realized by Lakatos, and there is where crucial deviation from this radical Kuhnianism is going on. When such an ad hoc hypothesis cannot be independently confirmed, by no means at all, for decades and decades, where people try to find independent evidence for the ad hoc hypothesis, to remove its ad hoc status. If that doesn't work, then particularly the younger generation of scientists lose their trust in the theory core. So you see, the theory core cannot strictly be refuted, but of course it can be gradually weakened too. So they lose their trust, so it becomes just very implausible that there is this Vulcan there. Right? It's very, very implausible. So there must be something, if it's not the perturbing planet, the cause of this deviation, there must be something wrong, either in the core laws or in the special gravitational force law. Yeah? That follows. So younger scientists then start to think about alternative theory cores, and in this case it was Albert Einstein who developed, also based on various other empirical facts, his general relativity theory. The general relativity theory says that in regions of space where you have a very strong gravitational field, and that is of course the case for Mercury, because it is the closest planet to the Sun, so there the gravitational field of the Sun is strongest, right? And in these regions of the space, the geometry becomes banded, right? And that causes deviation from the Newtonian predictions, which assumes an Euclidean space. So it was possible to explain the deviation of the orbit of Mercury by means of general relativity theory, and that was a great success, but in this case, not of Newtonian mechanics, but of general relativity theory. Okay, so you see here that what you see here are 2 points. First, this major point which is called holism of theory testing, or holism of falsification, after Pierre Duhem. Pierre Duhem is a French philosopher of science and physicist who is really famous for having discovered this as, I think, the first, well, in the history of philosophers of science. So he said, what you see first from this, there is no experimentum crucis, which can really force the defenders of a theory to give up the theory core. So that is how you must formulate the non-experiment crucis theory. Of course there is an experiment crucis, an experiment which forces you to change something in your theory version, including the periphery, but no experiment can force you to change the core. That is what is called holism of theory testing, no experimentum crucis. And just for terminology, as I said, if you change the periphery of the theory, you speak of a new version of the same theory. I already said that. And if you change the core of the theory, then you speak of a new theory. Okay. But the second thing is what Lakatos brought out. The second major conclusion. Lakatos argued against Popper's naive falsification model. There are 2 points. The first point is, And this point is where Lakatos agrees with Kuhn, right? Theories can always protect it from a conflict with experience, as I said it already, by the introduction of ad hoc auxiliary hypotheses which proclaim the existence of disturbing factors. That is one thing. We have seen that. It follows from these ceteris paribus assumptions which you always need. But where Lakatos did not agree with Kuhn is that as a result of this fact, theory cores are incommensurable. No, there's a weak methodology, there's a weak methodology, there's a weak methodology even for the rational revision of theory cores, right? And that is also what Lakatos did, what Lakatos generated. He came up with the following rule, with the following methodological requirement. He said, ad hoc hypotheses are legitimate as long as they do not decrease the empirical content of a theory. That is his first requirement. So whenever you come up with the ad hoc hypothesis, you must not only just claim, well, Newtonian mechanics doesn't apply to Uranus, or it doesn't apply to Mercury, that's all. That would be a really decrease of content. That is never allowed. But that Leverrier didn't do. Leverrier didn't just say, Newtonian physics doesn't apply to Mercury in the second case, in the second example, but he came up with a positive hypothesis, a disturbing planet called Vulcan. So that is the first requirement was met, right? And Vulcan explained this deviation, but in an ad hoc way. But the second requirement is, after some time, the ad hoc hypothesis must increase the empirical content by Lakatos calls this empirically progressiveness. So it must become empirically progressive, namely in order to become independently testable. So the second requirement is that every ad hoc hypothesis must, at least after some time, right, be independently testable. Otherwise, you really cannot say that this hypothesis, it doesn't lose its ad hoc character, so it never gets really confirmation. Because just by the fact that it explains this deviation from the data, that is not enough to confirm it. What you need is an independent test. That is the second requirement of Lakatos. And obviously the second requirement is not met by the Vulcan hypothesis, because there has never been found an independent test of that, right? And therefore, there was rational reason then to doubt the core of classical mechanics and to prefer and to revise physics in general and to prefer the relativity theory as a theory with a new core. Of course, what has to be mentioned here for non-physicists among you, that no one ever doubted that if that is a domain of relativity theory, the domain of application, and that is a domain of Newtonian classical theory, then the classical physics is still valid in a certain domain of applications, where it leads almost to almost the same predictions as relativity theory. And this is a domain of moderated sized object and the domain of moderate velocities. Only if you go to the domain of microphysics, say here where you speak about atoms or tiny particles, you are in the domain of quantum mechanics. And if you go to very high velocities, like velocities which are close to light velocity, then in that domain you need relativity theory. So the revision, the correction that the relativity theory implied for Newtonian theory just concerned a special domain, right, of applications. But in that domain it was clear that this paradigm of classical mechanics has to be given up. And that was something which was not a matter of political structure only, or a matter of political debate as Kuhn would have it, but it was a rational development following these methodological principles. Okay, any questions to this part? Yes?
So Lakatos says the ad hoc hypothesis cannot decrease the empirical content. But what if we have a very strong theory and it turns out that some of the consequences are wrong? But we might have some reason to believe that a weaker form of the theory might still be true.
Yes, that's a very good question. In my philosophy of science book, has come about that question. It means that Lakatos' rationality principle can come into conflict under, so to speak, unlucky situations. So he says that if you have a theory which comes in conflict with certain data, so if you just restrict the theory, say, well, it doesn't apply to this data, right? That is all what you say. Then it would really be this development, Lakatos calls it degenerate development or degeneration. And in this respect, he's right. Of course, for instance, when classical physics was applied to atoms, and you had this strange consequence that an atom should not be stable if you apply classical mechanics to it, because it would always lose energy, and you need this Bohr's postulate. Before that time, you just could have, and some people have just drawn this diagnosis. It doesn't apply to atoms. Newtonian physics doesn't apply. You have to exempt them. So this is a degenerate development. You agree probably with that. But Lakatos didn't tell us anything about a situation where this is the best what you can do at the present time, right? So if really nobody has a better theory, right? Maybe the restriction of the theory is just the best thing that you can do. And that's how Lakatos should be interpreted. It may be that a degenerative development which violates these rules is just the only possibility which is left. In that case, well, you have to eat the pudding, so to speak, and it's not there. But you're right, yeah.
I'm also thinking of an example.
But just to say that, Lakatos' rules should be understood as heuristics. He also understands this as heuristics. So the heuristic means be never satisfied with such a development. Try to enlarge the empirical content again. Do something with this anomalous data which you cannot explain. Even if Lakatos, you would even say, even if it is an ad hoc hypothesis, try out some ad hoc hypothesis, right? This is the best, this is what you should do. You should not be satisfied with it. Okay, yes?
The case I'm thinking of is where we assumed a deterministic law and we find some evidence against that, and now we say, okay, maybe it's just a statistical law. And this might be reasonable, right?
Yeah. Yeah.
But it decreases empirical content, of course.
Yeah, that is true, yeah. That would also be a good example. Yeah. Although Lakatos spoke about theories, right, and theoretical concepts. Right? That was his. Okay, I would say we are at the end of the time and at the end of the lecture. Thank you for the discussion. Until next time, thank you.